So let us calculate the number of states that the free electron can occupy. Now, because of the uncertainty principle, the smallest combination of space and momentum of the free electron must obey dx dp is equal to h, where h is Planck's constant. That means that the smallest volume that the electron can occupy would be dx cubed. Sorry, this should be a p here, not an x. It's going to be then h cubed over the dp cubed. So let's call this the smallest cell of space that an electron with a given momentum between p and p plus dp can occupy. Right? This would be a cube of space of size equal to dx. So I'm using a different color. So you have an electron in here, in this space, and then this electron has momentum between p and p plus dp. Now, the number dn of such cells available is the volume VE that is occupied by the electron distribution. dn is the number of such cells, dx cubed is the volume of one of the single cells, and VE is the volume occupied by the electron distribution. So we can solve this for dn, and using the expression of the uncertainty principle, write that in terms of dp. Now, because of Pauli's exclusion principle, each of these cells can hold two electrons, one with the spin up and one with the spin down. That means that the number dGe, that's the degeneracy of the free electron, is equal to twice the number dn, because each one of these cells can occupy two electrons. Now, this number is infinitesimal because it captures only electrons with momentum between p and p plus dp. So for the total number of electrons, then we need to integrate in momentum. If we assume spherical symmetry in phase space, we can then write that d3 d cube p is equal to 4 pi p squared dp. And the volume of the electron distribution then is the inverse of the number density. Now, because this number is infinitesimal, it gives us only dni plus 1, not the full number of ions in the upper level. Can write this then as a differential of the number of ions in the upper level, the ionized state, over the number of ions, atoms in the ground state, is equal to Gi plus 1 times dGe, the differential of the degeneracy of the electron, over Gi, then the degeneracy of atoms in the neutral state, and the exponential then of the energy in the upper state, the ionized state, minus the energy in the ground state, the neutral state. Now, if the ionized state, in the ionized state, the electron is unbounded, thus the energy Ei plus 1 is simply the kinetic energy of the free electron. And in the bound state, the electron had energy minus chi, where chi is the ionization potential. You had an electron in the ground state, it jumped not to an upper state, but it jumped to a free state. So what you have then is the ionization level, the ionization potential, that is chi, plus the kinetic energy of the free electron, which is p squared over 2m. So in fact, the energy I plus 1 minus Ei is equal to p squared over 2m plus the potential. So substituting this, you have then p squared over 2m plus chi in the difference of the energies. And if you substitute now the expression for the differential of the electron degeneracy, this expression still only gives the infinitesimal number of states where the free electron has momentum between p and p plus dp. We need to integrate this in momentum to find the total number of states. That means ni plus 1 over ni is equal to 1 over ni over the integral of the number of states in the ionized states, which is going to give us Gi plus 1 over Gi times 8 pi over the number density of the electrons over the cubic Planck constant times now the exponential of the ionization state over kT, and now the integral of all of the possible momenta. So this is a definite integral. Turns out that this gives you square root of pi over 4 times 2m kT to the power of 3/2. So you can substitute this, and then you find Ni plus 1 over Ni is equal to Gi plus 1 over Gi times 2 over NEH cubed exponential minus chi over kT times 2 pi m kT to the power 3/2. And we can express the ratio in the left-hand side in terms of number densities instead of total, dividing both sides by the electron density, to finally find Saha's ionization equation.